this computer. Today, I'm really pleased to introduce to you Dr. Rob Diehl, who's going to be presenting to us today on the response of flying animals to utility scale photovoltaic solar facilities. A little bit of background about Dr. Diehl. He got his PhD at the University of Illinois in 2003, followed by an NSF postdoc, which led to a faculty position at the University of Southern Mississippi. He accepted his current position as a research ecologist with USGS in Bozeman, Montana in 2011, where his work really follows three basic themes. One is understanding the behavior, ecology, and conservation of migrating birds. Two is determining how flying animals may be influenced by anthropogenic activity, especially in relation to energy development. And finally, advancing the remote sensing technologies biologists use to study birds and other wildlife. So I'm going to go ahead and turn it over to Rob and let him tell you a little bit more about his background. And again, thank you, Rob, for joining us today. We really appreciate you offering your time for the webinar series.
Yep, no problem. My pleasure. I think you've got the background covered. I won't bore you with any more of that business. And so we'll just get right down to it. And I apologize in advance, by the way. I'm fighting an illness, and so you'll probably hear myself. I ran out of cough drops yesterday, so you'll probably hear myself clear my throat repeatedly if you haven't already, and I apologize for that in advance. So I want to acknowledge my co-author here, Todd Preston. He's also with USGS here in Bozeman and aided in some of the data collection and analyses. So a little background on this issue of avian mortality associated with solar facilities. There was a report that came out in 2014, really motivated by fatalities that were being observed at the Ivanpah solar concentrating facility in California. And in the course of investigating the avian fatalities associated with that form of solar energy generation, which is really different from what we'll be talking about today, Kagan et al. Acknowledged this notion that vast fields of, in that case, heliostats, which are essentially just large mirrors, but also we might embody into that solar panels, may be indicative to flying animals as water bodies. And this was the sort of the first notion of this so-called lake effect that birds may be perceiving as they're moving through these, in this case, arid landscapes. And perhaps seeking oases or some other form of refuge during their movements. And this notion was sort of supported by the presence of a fair number of birds that are water associated or water obligate birds, sort of appearing as fatalities in these solar facilities. So that was 2014, and since then. And I have to acknowledge one of my co-authors, Carl Kostic from West Incorporated, who provided the content for this slide and is also a collaborator on this project. And I will not be speaking about his component of the project, nor that of Bruce Robertson's. He's at Bard College. Carl examined fatality, and Bruce examined solar cues, and we'll touch on that just briefly, but I'm not going to be talking about that specifically here today, although I have some of their materials with me, and we can get into that if the questions go that way. So anyway, since that time, fatalities have continued to be documented at solar facilities across the arid Southwest, and this is a paper by my colleague Carl documenting this. And you can see the sample sizes, vary, pretty considerably, from one site to the next here. And so we do seem to have at least some kind of problem emerging associated with avian fatalities linked to these solar facilities, at least in in the arid Southwest. And that led to sort of the genesis of this project, where we're examining this lake effect hypothesis, which I'm defining here as this, that utility scale facilities, these large solar facilities, attract birds by simulating cues that birds might associate with, with water. And we, in the course of this project, as I already alluded to, kind of broke this problem down into three parts that match this process, if you will, that birds may go through from one, detection of the solar facility and its association by birds with some place that they want to be. We're assuming it's a lake. It could be some other form of oasis, due to the lake mimicking a cue that would be linked to a lake. And so in particular, polarized light. So Bruce Robertson, again at Bard College, was charged in this project of with studying whether or not birds can detect polarized light, just to ascertain whether or not that would be a reasonable sort of cue modality that birds may be using in associating these solar fields with water. Following this, this detection by birds, there's a flight behavior adjustment. So birds that are moving along, of course, are going to have to move toward the facility in some fashion. And that's what we're going to be talking about today. And then finally, there's, how animals arrive and interact with these solar facilities, potentially leading to fatality. And that was the role that Carl Kostic played in this project. And again, we're not going to talk very much about that part of it today. But again, if the questions go in that direction, we can certainly delve into that material. So the middle part of this here, in dealing with the flight behavior, we're trying to link animals' perceptions of potentially of these solar facilities as lake-like, if you will, or water body-like, with fatality by looking at this at these behaviors of animals in flight over solar facilities. And so there are essentially two things that animals can do. They can reorient, which I'm defining here as, change directions laterally, essentially left or right, preferentially toward a facility, or they can change their altitude. They can descend, or they can do both. And so where did we study this? Well, I'll just say that, to take a step back again, this attraction to polarized light cue was actually studied in New York State. It's very difficult or probably impossible to make such a determination for free-flying animals that are, hundreds of meters above the ground, which most of the animals flying over these facilities are. And so in order to gain control over animals' cues, Bruce actually engaged in feeder and water bathing controlled experiments in New York State to ascertain whether or not birds exhibited attraction to polarized light. They do, and we can again delve into that if we want to. The latter two parts, looking at flight behavior and examining fatalities, did take place in Southern California. The fatality sites are identified here in green, yellow, red, purple, and green, yellow, red, and purple. And we looked at flight behavior in relation to two of these facilities, these solar facilities, Seville and Desert Sunlight, which are really very, very different places. So that's the where. The when was during, for this work, looking at flight behavior, and I'm doing some fatality monitoring, occurred during September and October. My component, the component associated with flight behavior, occurred largely in October. And this is consistent with historic patterns of avian mortality as they've been observed across at least 7 solar facilities, as we see here. Disproportionate mortality occurring in fall. It's striking to me that we don't see a signal here in spring, given that these are the migratory movements. And that might be evidence in some way that the direction of movement is potentially highly relevant to perceiving these facilities as water bodies. And we'll get into that some later here. So The work that I did was conducted at two places, again, Desert Sunlight and Seville. The map on the left outlines the areas in the center and right. And in each case, we have the solar facility, which in Desert Sunlight, the center image is located in the upper left corner of that center panel. And in the case of Seville, toward the lower right. This was a radar study, and we were using portable radars to identify movements of animals, both laterally, that reorientation phenomenon, and vertically, so ascending or descending in altitude. And the sort of yellow circle indicates the radar coverage extent associated, and we're looking at the middle panel here with Desert Sunlight. And you can see that it covers probably the northern half of the solar facility. And then the radar coverage associated with detecting vertical movement is kind of represented by that orange dash. You can think of it more as taking a slice or a cross section, if you will, through the movement layer, through the airspace, to see how animals are sort of transiting in altitude. Associated with each solar facility, there was a control area. And for Desert Sunlight, you can see that was to the southwest. And for the Seville facility, that was to the north. It's also worth noting, I think, in these two cases, that the landscape context, while arid, is very different. The Salton Sea is a considerable body of water, relatively close to Seville, about 20 kilometers away. Whereas Desert Sunlight is much more isolated in relation to water. There are small water bodies nearby, but certainly nothing to the extent of the Salton Sea. Also, Desert Sunlight is a large facility. It's 16 square kilometers, whereas Seville is much smaller, covering just a couple few. So data collection here and processing. Again, we're gathering data sort of in the horizontal domain, and we're doing that with a radar as depicted here at the right. And so we incline this antenna about 30 degrees above the horizon, and it rotates, sweeping through a sort of a cone of airspace, literally detecting almost every flying animal that's moving through. Bird, bat, insect. Insects as small as the size of the tip of your pinky finger can be detected at 2 or 3 kilometers, and so it's really incredibly sensitive. And we're getting a picture of this migratory, or I should say, not just migratory, but movements through these areas 24 times a minute. And so after we do some processing on those data, we found that in the horizontal domain here, we ended up detecting 6.7 million targets, million flying animals. There was relative balance between the treatment control areas for Seville, not so much between Desert Sunlight and at Desert Sunlight. And so we're not entirely sure why that is, but the analysis tries to control for abundance concerns. In the vertical domain, we use a different antenna, and we rotate this antenna, the radar on end, as you can see in that image again to the right. So the maximum altitude of detection is 1,500 meters, and everything else is kind of the same in terms of the refresh rate. And here we detected, about 4.4 million flying animals with good balance between abundances and treatment and control in both cases here. Data processing, we have a lot of ground clutter, and so the ground just poses noise to the radar, and we have to try to pull that out. And we also work to discriminate animal types, primarily vertebrates from invertebrates, which really boils down mostly to birds and insects in this area. And it's not to say that there aren't bats, but the birds very likely outnumber them by orders of magnitude. Target discrimination posed a considerable challenge, and we'll be talking a little bit about that later. And then finally, we break the analysis down and get specific about what we're actually looking at, what the relevance of the time of the day and track length and the height of the animals and so on in relation to attraction. So there is some assumptions behind all this, that in laterally, across a wide swath or the coverage area of the radar, that we have a relative absence of non-effect related behaviors. That animals are distributed in non-effect, which is to say non-solar facility related ways, relatively equally. We use these two radars, the one that's detecting animals in the horizontal domain and the one that's detecting animals in the vertical domain. They're mounted on different trucks, and we swap locations of the trucks for a given, associated with a given facility between the treatment and the control location. And we're kind of assuming that swapping did not inadvertently oversample, say, the movement of a particular biota through an area, for, say, only the treatment area and not the control area. And so we tried to rotate the radar every 3 or 4 days. And so we're feeling that we're not getting any, it's unlikely that we're getting any sort of temporal bias being introduced in the data here from that. We're also assuming that relatively similar species types occur between treatment and control areas for both facilities. And finally, getting back to this really challenging target discrimination, that ground speed functions as a reasonable proxy for animal type. And here what we're suggesting is that the relatively fast moving animals are vertebrates, mostly birds, and the slow moving animals are more likely to be insects. This is generally true, is generally shown to be true. That's not to say that there aren't outlying situations, but by and large, insects, with some exceptions, are moving with prevailing winds, whereas vertebrates have the capacity to add their considerably add their own power to whatever wind support they may have toward moving themselves across the landscape. So a pernicious problem in all kinds of radar work, almost literally all kinds of radar work, is aspect bias. A bird birds and bats and insects are sort of oblong in nature, and that's kind of represented by this oval here. And what that means is that the radar is located here, and when it sends out its energy to detect things in the airspace, the broader side-on view of an animal is producing more radar returns than the front or tail view. And that's being represented here by an image that was captured by the radar. This is actually out of Colorado. And the radar is located centrally here. And you can see that this is kind of radially symmetric along this axis, where we have really strong detections of animals here and here, and relatively few here and here. And this is because of this aspect effect. So when we go to try to quantify effects, we have to make sure that we pay attention to that we're comparing apples and oranges. And so I'll show you what we mean by that here in just a minute. So this lateral reorientation problem, are animals, changing their directions of travel to presumably preferentially attempt to occupy a solar facility. We have to pay attention to this aspect bias effect, and so we do so here by only relating areas that share the same color. Okay, so A is related to, this region of A. Distant from the facility is related to this region of A, closer to the facility. Likewise for actually B and C, and so in doing this, we're actually looking at the directions of movement. And so this is the treatment location, and we're looking at direction of animals from this region compared to this region, and we're subtracting from that what the directions are in the corresponding control area. And again, this is across a month of time. So this is kind of average throughout this time frame here. And what we're the prediction would be that if we have favorable movement toward a facility, then that would show up as a positive bias in the treatment area relative to the control area. And so that's what we see here. And I guess I would draw your attention let's see, yeah, just the bottom part of this figure. Ignore the top part of this here for the moment because we're not going to get into that today. This is for slow moving animals that are moving less than 5 meters per second. So these are what we're presuming are more likely to be insects. And I've divided this up into diurnal areas or diurnal timeframes and nocturnal timeframes. And each of these rows here, A, B, and C, theta A, B, and C, represent each of these colored regions here, A, B, and C. And what we see in this case is the presence of positive change in direction, which is predicted to be associated with movement relative to controls toward a facility. And that's occurring during the day, whereas at night we have a more mixed result. And this is what the result looks like for very high speed animals. So we're supposing these are more likely to be vertebrates. And that dichotomy of response actually breaks down. So in terms of what we think are more vertebrate-like animals, and again, there's always a caveat lying over this vertebrate versus invertebrate distinction here. But anyway, what we think are more likely to be vertebrates seem to be exhibiting less evidence of descent towards solar facilities than the slower moving, or what we would consider to be perhaps more likely to be vertebrates. So not much of a response that we're detecting here, or not much evidence of it. Notice there's a big gap here in the speeds of the animals that we're analyzing, greater than 14 meters per second, less than 5 meters per second. We're treating this big region in the middle, 6 to 13, as ambiguous. And so we're I hesitate to make an attribution in that regard. Frankly, I even hesitate to make attributions at these extreme ends. So looking at the movement in the vertical domain, whether animals could be attracted not laterally, but through descent. We're looking at, again, radar data of animals moving, ascending or descending. And this is kind of we have the same aspect problem that we have to deal with these data that we have to deal with, in the other data set. And what we see here, the radar is located here. This is the ground. This is the maximum range of detection, this green line here. And animals are always in some form of ascent, descent, or level flight. So it really almost any time of day or night, if you were to sample the airspace, in most cases, you're going to be finding animals that are doing, one or the other. And in this case, we have this aspect problem again. And so when the radar sees birds or insects ventrally, it's going to produce more radar echo than, which is to say for animals that are climbing. It's going to produce more radar echo than animals that are descending sort of nose toward the radar. And again, this is the same problem that we had before, just along a different axis. Whereas animals that are flying away, we are more inclined to see, oh, I'm sorry, I got it backwards. These are animals that are ascending, we're seeing ventrally, that are approaching. Animals that are descending while they're moving away from the radar, we're seeing ventrally and are going to produce more echoes. Whereas those that are ascending while moving away are going to produce less echoes. So this is a known problem. And it produces this kind of bias in the data. These are real data from the control area at desert sunlight. And for animals that are generally moving north, which is to say left to right, or south, in this case, as depicted here, right to left. And so we can just focus on the southbound for the moment. Notice our vertical axis here is ascent. And so we're looking at these ascents and descents. And we have a disproportionate amount of ascent occurring for animals that are moving toward the radar, and a disproportionate amount of descent for animals that are moving away. And this is why that is. So that's an artifact. It's not real. And we would be misinterpreting the data if we were to say, if there's a solar facility right under here, which by the way there is, this part of the radar coverage, oh, look at all the descent that's happening, this must be attraction. No, that would be wrong. There's this background bias that we have to concern ourselves with. And you can see a mirror image of that happening here in the northbound case. We do that by comparing our control observation to the treatment observation and looking at the relative proportions of animals engaging in different behavior. And that's what this relation is here. We can exercise this. It accounts for this aspect bias. It standardizes the results against the controls and is independent of abundance. So we really don't need to concern ourselves with the fact that we might have more animals over here versus over here, or that the control area differs in abundance from the treatment area. We're kind of accommodating that here in this relationship because we're looking at a proportion. Okay, so results on this. In the condition of animals that are moving toward the south during the day, we have a proportion descending over the solar facility. Again, this is relative to controls for both areas, desert sunlight and Seville, that ranges between, on average, to about 12% to maybe 23 or 24% of animals that are exhibiting behavior that's consistent with descent towards solar facilities. We don't see that pattern when animals are southbound, but they're doing it at night, or in any case, day or night, northbound. So the most pronounced effect is during the day for animals that are moving toward the south. Now, you might say, well, it's October, most of the animals are moving south, perhaps because this is migration, this is true. But there are almost always animals moving every direction in any given season. And so we capture considerable amounts of northbound and southbound movement during the day and the night, but especially during the day, since most animal migration occurs at night. So we try to look at speed a little bit and ascertain whether or not there was an association or relationship between the speed of the animal that we were seeing and its propensity for descent over a solar facility. And so we're sort of breaking these data down by speed. And there does seem to be a tendency for slower moving animals to exhibit what we would consider to be a greater propensity for descent relative to higher speed animals, but in no case was descent absent. So all speed classes of animals are exhibiting some propensity to descend toward these solar facilities. It's just that the proportions differ. Does altitude, does the propensity for descent vary with altitude? This is a bit trickier in a way to get to, because the way that altitude data are gathered by radar introduces a bit of a bias that's challenging to try to account for. So while we might say that these mid altitudes are consistent with the greatest proportion of animals descending toward the solar facility, I kind of treat this with a bit of grain of salt, given that there are again challenges in the way data are gathered in the vertical domain that I guess leave some question marks hanging over this. So I would say, even though this is the, I guess the statistical result, I would be hesitant to say that we have an effect that would be associated with height that we feel confident in at this time. So getting back to this observation here, we wanted to dig in a little deeper as to what might be happening during the day for southbound animals. And so we modeled the change in descent as a sort of a normal, you can think of, I just call it a Gaussian function, but like a normal curve. We're seeing it happen during the day. We're not seeing it happen so much at night. And so this is a normal function. Again, everything is in proportions. And so the absolute numbers of animals are accommodated here. We tried doing this adding skew. In other words, do we see a disproportionate amount, say, of descent during an early part of the day or the latter part of the day? Those models did not perform any better than using a normal Gaussian, and this is what that looks like. So for animals in radar coverage that have short tracks, we see at both desert sunlight and Seville for southbound animals a strong tendency for mid, in the case of Seville, to later afternoon descents. And those proportions tapered off considerably in the evening hours or the nighttime hours. And the reason I draw attention to track length here is because for data that are gathered in the vertical domain, and this is what the radar coverage, by the way, looks like if we were looking sort of down from the sky. But it's really slicing this cross section through the airspace like this, but it kind of has these triangular shaped patterns to it. And animals with really short tracks are able to pass through the beam almost perpendicularly, in this case, east to west. Whereas animals with longer tracks almost have to be moving more in a north-south direction because they're just able to dwell within the beam for a greater period of time. There are exceptions on both sides of this depending on the speed of the animal, but this general tendency is true. If we look at just longer track length animals, which is to say animals that are more likely moving in a north-south direction, these patterns are much more pronounced. And the proportions of animals that are descending is greater, but the timing doesn't change. And so there's still this sort of curious discrepancy between when the mean peak of descent towards solar facilities occurs at desert sunlight versus Seville. And it's about 2.5 hours more. And so we'll talk a little bit more, about that, in a second. But I want to sort of take a step back and go through some conclusions on this real quick. In terms of reorientation, I'd say it's kind of inconclusive for faster, more bird-like animals. If anything, we didn't talk about some of those data, and that's where the quote inconclusive comes from. But the evidence for that for faster animals is somewhere between relatively weak or non-existent, whereas it's much stronger for slower moving or what we would call insect-like animals. There is this assumption, which is especially, I think, potentially an issue at desert sunlight, of whether or not animals are uniformly distributed in the radar coverage. Desert sunlight is unique relative to its own control area in both the locations associated with Seville, the treatment and control area associated with Seville, in that it's surrounded by mountain ranges to the northeast and west. And this may have the effect of channeling animals in ways that introduce bias into lateral movements that could affect the outcome of analysis like this. So that's one possible explanation for what we may be seeing there. In terms of descent, it was really pronounced among diurnal southbound animals at both locations. And keep in mind that more so at Seville and desert sunlight, but very pronounced in both locations. And which is interesting in a way because they differ dramatically. They differ in their landscape context. They differ in size. They differ in other ways that we'll get into in a minute. Yet this pattern persisted, it was the same. It was most pronounced again for slower animals, but present among all. Again, mid-altitude animals show greatest propensity for descent, but we've talked about this coverage bias issue that could explain that. And I think most interesting, there is a pronounced Diehl response. In other words, there's a midday peak that occurs either, like I said, midday or early afternoon, and is more pronounced for these longer tracks as we just saw. And it makes us wonder. It makes those of us on the team and others whether this might be associated with a light cue, since the importance of track length seemed to be relevant in terms of the magnitude of the response, which is to say the importance of the animal's track being oriented more toward the south. And so since polarized light was examined as a cue as part of the project, polarized light is associated with open water bodies, polarized light. Other parts of this project have shown that birds are able to detect polarized light, and in the studies that were conducted are attracted to features associated with polarized light. And so we're seeing this similar descent response at both facilities that I mentioned, despite these differences in size and context. And I wanted to bring in another observation here. This is the southbound observations from Seville that we saw before. This is the corresponding northbound observation, just below it. And so it's the same analysis just applied to animals moving north during, during this 24-hour period. And we see a relatively, a limited to no response during daytime hours. We would expect that if animals were responding to, say, midday heat and seeking refuge from midday heat, that would happen in the northbound case as well, but it's not. And I also draw your attention to one of the earlier slides in the presentation where we saw disproportionate amounts of mortality associated with fall, which is characterized by predominantly southbound movement by vertebrates, as opposed to spring, which showed no difference in fatality relative to summer or winter in this area. So these observations, those observations presented earlier in the presentation are kind of consistent with animals' response to some kind of solar cue. And given that we're finding birds are able to detect and respond preferentially to polarized light, that may be the cue that that we're dealing with here. So that's there's a lingering question as to whether or not that's actually the case, because it's very difficult to know the behaviors of especially intrinsic to the animal when they're in loft, as I was saying, aloft several 100 meters above the ground. But I want to draw your attention here to another discrepancy which we talked about earlier, and that is looking at this bottom panel, a difference in the timing of these modalities. Here they are overlaid with one another, and so the mean time of peak descent towards solar facilities at Seville was close to noon, where it was 2.5 hours later at desert sunlight, and the effect is really pronounced in the data. And so I call this unsatisfying. But it's the closest we've been able to come to, I think, understanding why we might be seeing this discrepancy. And it presupposes, first, that we're right about these solar cues, that animals are responding strongly to solar cues. And by the way, when water polarizes light to a certain degree, solar panels do it even more strongly. And if animals' responses are scaled to the magnitude of polarization, then it might be the case that solar panels elicit through a polarization cue an even stronger response of attraction than water bodies. That has been proven to be true for insects. Whether that's the case with birds or not, I think remains unknown. And so let's also assume that directions of travel influence the likelihood of response. We've kind of already seen that. We've presented a slide that are some data that suggests that when we look at animals whose directions of travel are oriented more north to south and laterally, we see a greater propensity for descent to solar facilities. So with those thoughts in place, and then also given the fact that Seville and desert sunlight, they do differ greatly. We're kind of zooming in here for both Seville and desert sunlight on what the vertical radar cross section looks like. We were positioned here toward the periphery of the Seville facility, whereas more centrally located with respect to desert sunlight. This is for practical reasons. We couldn't always put the radars exactly where we wanted to. So there is difference in where the data are collected with respect to these solar facilities. The solar facilities also differ in the way their panels work. Desert sunlight is one of the few facilities that has just fixed angle panels. They're angled at about 25 degrees. They tilt south, and that's it. Seville's panels actually rotate to follow the sun. And when the sun is in its zenith, the panels are actually flat relative to the surface of the earth. And of course, as the sun, sets in the west, the panel will rotate to follow that. So there's a lot of complex interactions happening between, that consider the location of the radar, the position of the sun, the directions animals are traveling, the orientation of the panels. Abundance could play a role. I think it's less likely. And the closest I can get to explaining this is that there's a complex interaction or interplay between all these factors that creates circumstances that are idiosyncratic to each of these solar facilities as to when animals that are in the radar coverage area are exposed to the most polarized light, and that we may be seeing a reflection of those idiosyncrasies between those facilities in the differences of when animals are responding throughout the Diehl, as represented over here in the upper left. Just a final word on target discrimination. We've since made progress in this area. Usually the radar's beam is rotating. And when it's rotating, it doesn't spend any time dwelling on the animal. It's just it really just gives us a brief blip. And we stitch the blips together across tracks, across rotations of the radar to create tracks, which tell us if an animal is descending or moving left to right or what have you. If we can position the antennas in a stationary fashion and let animals pass through it just sort of passively as they're moving along, then we can capture actual segments of wing beating from birds and insects during that time in the radar. And that actually produces patterns that are analyzable. So it's often the case with birds that they have this flat coast, flat coast, flat coast pattern when they're flying, migratory birds in particular, songbirds. Not all of them do this, but many do. Whereas insects, to our knowledge, are just flat continuously and at a much higher rate. And so we can apply some signal processing techniques to these kinds of data to make this distinction with pretty high reliability. Here are just 4 examples right here. Time is on the x-axis, and we have frequency, and this is the frequency of the wing beat rate on the vertical axis. And for birds, you can see that the fundamental frequency, the strongest one, is about 20 beats per second, maybe 18. Same thing over here. Whereas for insects, it is often much, much higher. There is some overlap from the larger insects, but there's much less overlap in wing beat rate as opposed to speed, for example. So, we're believing that moving forward, and these methods have been adopted by, a few others, throughout the world who do this kind of work to make these distinctions, that we can, moving forward, apply these kinds of algorithms to be much more confident about the target types that we're detecting here moving over airspaces. Incidentally, in this lower right corner, we're actually detecting 2 animals at once, essentially right next to each other in the airspace. And so these signal processing methods are actually enable us to have a much more nuanced view of what the radar is seeing than the relatively coarse approach of just letting the radar rotate and detect and count blips. So that's it. I'd like to acknowledge these people. Again, my primary collaborators, Bruce and Carl. Carl was assisted by Danny Reiser Espinosa, also with West. Funding is primarily through California Energy Commission, but with considerable support from the solar energy industry. And I'd like to point out among the administrators here, David Stoms, who is our sort of project officer with the California Energy Commission. He's been with us through a long haul on this project and had a lot of patience. So I think with that, I can stop, and I'm happy to take questions.
Thanks, Rob. Super cool. I'm just like sitting here with so many questions going through my head as you've been and thinking about new research experiments that can come off of this after you guys start analyzing things. We did have, I don't know if you addressed this, but Doug was asking about the elevation difference between the 2 solar facilities. Did you mention that in your talk?
I didn't, and I can't remember what it is off the top of my head. Yeah, actually, I do. Now that I think about it, Seville is 5 meters below sea level, which is the first time I've ever done, had a project site that was below sea level, especially given that I live in the mountains. And I think Desert Sunlight is on the order of maybe 170 meters above sea level. So many of us are more used to thinking in terms of feet. So it's it's like a 600-foot difference. That could be meaningful in relation to what the target types are. But that also presupposes that when animals are moving through these landscapes, that they're not, in the course of their movements, in some ways contouring. There is some evidence of that, from the literature that they're following contours, and at the same time, but they do that loosely. So it probably depends on what the overall context of the landscapes are. So desert sunlight again sits in a little bit of a valley. There are mountains to the east, west, and north. If animals are compelled in their movement through the area from north to south to gain altitude, and they remain at those altitudes for some period of time, then that could introduce a terrain-based bias in the altitude distribution of the animals that we were seeing when comparing desert sunlight, to the likes of Seville.
That makes sense. Doug, did that answer your question?
Yes, it did. Thank you.
Brandon, we may as well go ahead and let you ask your question live, if you don't mind. Go ahead and unmute yourself.
Sure, thank you for the presentation. On an early slide, you showed the different types of birds like water-obligates and whatnot, water-obligate birds and whatnot. I think it was like the third slide or so at the beginning. But on some of the graphs, there was this orange column that said other birds. Yeah, let's see, I think yeah, that one right there, and maybe the next slide too. Like, what are the other birds, like, as far as a group of those birds, since they're the majority in some cases?
They're the majority in a lot of cases, and they're usually these perching birds or songbirds, as we're seeing. And my understanding is, this wasn't my work, that these are often thought to be residents, and perhaps not migratory. I don't know the details of what the seasonal behavior association with birds in the quote yellow of this are, but we're dealing mostly with the perching birds, the land birds. Yep. Mm-hmm.
Elise, would you like to go ahead and unmute yourself and ask your question?
Sure. So obviously we're talking about impacts with wildlife here. So many conservationists are concerned not only with the land use that these large solar facilities use, but also their impacts to wildlife and birds. So how do you, just when you're out and about in the public, how do you respond to these concerns? And do you kind of shift the conversation to distributed energy resources or energy on site, or how do you handle those questions?
Well, I don't get questions outside the data very often. And in fact, USGS refrains from taking a position on these kinds of things that are outside the data. What the data suggests here is that we do have animal fatalities associated with facilities, that the presence of water obligate and water associated birds at facilities seems to suggest that there is a water related phenomenon occurring, in relation to their mortality, that might be present for even non-water associated birds as well. I've tended to, I've been inclined not to use the word lake effect in some circumstances and refer to this more as an oasis effect. Believing that the channels of perceptions that animals have in relation to, seeing these facilities as oases may be well beyond just perceiving them as water. It could be perceived as shade. I mean, I don't know. One could perhaps, or maybe a source of food in some way. So the fatalities are happening, and one of the concluding elements of this research is to try to understand from what we've learned, are there things that we can do in terms of guiding siting or design, that can offset or reduce fatalities at these facilities. And so one of the analyses that's in our future is to take data like this, what we're seeing here in the slide right now, which was gathered outside of our project, and include data that was gathered in the project in terms of distributions of mortality, and try to determine, whether or not there are consistencies associated with, say, the size of the facility or the landscape context of the facility or the type of solar panel that the facility is using and so on and so forth, that might indicate some conservation measure that might be adopted. Don't put a facility in this location for these reasons, or don't build a facility in this way for these reasons. We're not close to that yet, but we're starting to gather the kinds of data that can inform on that kind of thing. In terms of the design of solar panels themselves, assuming that we're on to something in believing that polarized light is a cue that animals are using in associating solar facilities with water, to the extent that we can disrupt that cue, we might be able to prevent those associations from occurring, at the outset. And in so doing, try to limit, the impacts of solar facilities on flying animals. And there may be a variety of ways of doing that. The trick is to try to do that, I think, without interfering with solar energy generation. Otherwise, some of these solutions may not be very palatable or easy to get adopted. But there are a lot of unanswered questions in that regard, as to whether or not we can find a cue that would allow us to kind of interfere with an animal's perception of associating these facilities as some kind of oasis. That might dance around your question a little bit, but that's the best I can do.
Mona, did you want to unmute and ask your question? And if you have questions, folks, raise your hand and we'll try to get to you.
Yes, hi. Yeah, my question is sort of two-part. It's about altitude of flight. Just wondering if the north and the southbound discrepancy in the data was perhaps had any relation to what altitude the targets were at. And then the second part is also about the descent, like how much did they descend? Do you know that?
So in terms of the interaction between altitude and direction, we have not looked at that specifically. So it is entirely possible that, and let's think for the moment about daytime animals, because that's when we get the vast majority of northbound animals is during the day. We get a lot we get a lot of southbound and northbound animals during the day. At night, animals, are primarily migratory, and they tend to migrate at relatively high altitudes. And so there's probably a discrepancy between night and day in terms of the altitude distribution. I did not look at that within these data sets yet. But during the day, the motivation is different. Usually it's associated with, moving between foraging areas or foraging. And it's easier, in my mind anyway, to believe that behaviorally animals are engaged in the same kinds of behavior, whether northbound or southbound, and that their altitude distributions may not, didn't differ very much. We did look at a little bit at that during the day, and I didn't present anything on this, but I don't recall seeing any overt differences in that regard. To the question of descent, we didn't measure how many meters an animal descended or ascended. We had some ascents too. We can do that, but we did show in one of these slides, and let me just fast forward here. This is probably the best one to show. This ascent, this is an angle of ascent, and so this shows you what the angle that animals are taking when they're descending as determined by radar data. And as you can see, it can be quite extreme. Some of that is exaggerated by the angle at which the animal is actually entering the radar beam. And some of that is, of course, the animal descending. But all descents are descents and all ascents are descents. The magnitude of it can be an exaggeration. And so there's an element of ambiguity there that we can't quite resolve because of the way we gather these data. But absolute amounts of ascent and descent are in the data set, and we just haven't analyzed those yet.
We only have time for a couple more questions. Heidi, did you get your question sort of answered there?
Yeah, I just kind of was wondering if you thought, obviously there's still questions to be answered about how much this is impacting how much this is related to the actual mortalities, but what kinds of mitigation other than siting, angle of the solar panels, what are some other kind of mitigation things that would kind of benefit or alleviate some of this issue of the animals being attracted to the polarized light?
You know, outside, you know, paying attention to siting and surface treatments and how you know how solar facilities are constructed, I don't know. We didn't really talk about surface treatments, you know, much, but it may be possible to well, I guess we kind of did when I mentioned that we had talked about inhibiting, you know, polarized light. The challenge there is trying to do so while not interfering with solar energy production, and there it becomes an adoption issue. So, you know, I suppose in a sense the ultimate solution is not to build these facilities. That seems to be out of our hands. It's certainly outside the purview of my job. One of the other things that we're looking at, I hate to turn back to siting, but it remains an unknown question, is that, you know, we're seeing some fatality occurring in the desert Southwest that may be associated with the extreme arid conditions of these areas, the fact that some of them are highly isolated from other natural non-fatal oases. And it might be the case that as solar energy develops in other parts of the country, which it is, you know, I get calls, you know, from Florida and others, people are inquiring about, you know, okay, is this phenomenon operational over here? Is it operational over there? We don't know, because the landscape context for those facilities is very different. And it might be that, you know, if you build a facility in the vicinity of other kinds of oases that birds might be attracted to, you know, maybe fatality is reduced. Or conversely, if you're building a facility in areas that attract animals in disproportionate numbers, maybe the mere exposure could increase fatality. So for example, every solar facility is going to be tied in, or most of them are tied in some way to the grid with gen ties. And so there's a power line grade issue associated with many of these areas that might be a source of mortality. And I think has been documented to be a source of mortality for some animals.
We're almost at the top of the hour here, or we are at the top of the hour. So before everybody hops off, I want to make sure everybody knows that our next webinar is going to be on May 26th at 3 p.m. Eastern. It's going to be another USGS researcher, Jill Schaefer, who's going to be talking about tools for mitigating the behavioral effects of renewable energy facilities on grassland birds and waterfowl. So be sure you tune in and look for the announcements for that, May 26th at 3 p.m. Eastern. Got one final question here, and then we'll let you go. Rob, did you actually quantify how many dead birds you guys were seeing? Glenna was asking that.
Yep, and that was Carl's part of the project. It wasn't many. I want to say it was in the low teens total. They divided their time in that part of the project, and it was over 2 years. So several facilities over 2 years, and they divided their time looking for fatalities on facilities, but also offsite as well. And the reason why they did that is because we want to be sure that we're looking at above background mortality here, that we're not just seeing background mortality happening to be occurring in the solar facility itself. And sure enough, there were in desert environments and grassland environments, no fatalities outside solar facilities were observed. The larger data set associated with the first slide is probably the better one in terms of, and it was not associated with this project, is probably the better one in terms of enumerating, at least some of the mortality observed at these facilities to date.
Great. Well, I want to thank Rob again. Give him a hand for his presentation. And if there are additional questions, Rob, that we didn't get asked today, can we collect those and send them to you personally?
Yeah, absolutely. Yeah,
Okay.
absolutely. Yeah, by all means. Yeah.
Okay, well, great. Thank you again that was a fantastic presentation. We will try to get these webinars posted. We're working on that with Renewable Energy Working Group. But keep your eyes open, folks, for additional announcements, and feel free to reach out to anybody on the board anytime. We're also looking for speakers. So if anybody wants to speak at one of these webinar series, please send us your name and information, and we'll be sure to get you on the schedule, because we want to keep this going. We're getting a lot of momentum going on these. So again, thank you, Rob, and we'll see you guys all next month, okay? Take care.
Thank you all. Thank you. Thank you for the opportunity. Bye.
Bye.